Hello everybody and welcome to a new video, the last video of this series of exercises around the Fourier transform lesson. In this last exercise we will do, as it was in the previous exercise 9, an exercise where we get a signal at the input of a certain chain of operators and filters, and we are asked to find the output of the filter. Remember of the whole chain of filters and operators. Here, as I told you, what you have to do is go in an orderly manner and get the values of the signal in each of the points, intermediate points of the chain, and well, you will see that we'll find some interesting things. So the data that we have is the chain itself, but also we get the Fourier transform of the input x omega, which is this triangle function that you see over here, and also we get the value of the Fourier, the frequency transfer of this block over here. So also they tell us that we could consider for the whole exercise that omega c is much higher than omega m. Omega c is, as you can see, the frequencies of the frequency of these cosinus and sinus functions that multiply the signal at different points of the path, and omega m is the maximum width of the input signal in frequency. As you can see over here, the input signal is a triangle, and the maximum frequency of the triangle is omega m. So we should consider again that the frequency of the sinus and cosinus is much higher than the extension in frequency of this input signal, the frequency the triangle function. This is when this happens, you will see that we call this signal a baseband, narrow band, baseband signal. But this is something for the telco engineers and the telco guys that are listening to this video. Okay, so let's get started and let's calculate first y1 of omega, which is the value of the function after it has been multiplied by this cosinus. So let's go ahead and put here y1 of omega, which is our task now. So first of all, as there is a multiplication in time, we have to think on y in time, which is x of t time cosinus omega c. So this is a very important operation, which is called in the communications world as it's called modulation. So what we do is multiply the signal by a tone, that is how it's called the cosinus of a single frequency, and the frequency omega c, the c comes from carrier, because typically the signal, the cosinus that multiplies the signal to modulate it, it's called the carrier signal. So let's see what happens when we modulate the signal with a tone, with a carrier, like cosinus omega c. So if we do the Fourier transform of this, we will have the Fourier transform of x in omega times in the multiplication transforms in a convolution, but remember that the convolution gets a 2 pi factor in the denominator, and then we will have the Fourier transform of the cosinus that at this point of time we know very well. It's a pi and 2 deltas, one to the right and one to the left of the omega c frequency, where omega c is the frequency of our carrier. And what happens? Well, this pi and this pi they get cancelled, and we get half 1 divided by 2, and then we have the convolution of a x signal with 2 deltas. Remember that when we convolve a function with a delta, the result is just moving the signal to the point where the delta were. So the result of this will be 1 divided by 2, and then the signal x moved to where the first delta was, so it will be in omega minus omega c, plus the signal moved to where the other delta was, that it was in omega. This is wrong, this is a plus sinus here, plus omega c. Okay, so this is what happens with a modulation. Visually, what is happening if we draw y1 of omega, what happens is that around the carrier frequency omega c, what we do is we put over there the signal, the original signal that was in baseband. The signal baseband is called because it goes from 0 to a maximum of omega m. So the modulation basically does this. It moves in frequency, up in frequency, the original signal. Of course, there is another effect, which is it divides by 1 the original amplitude, and obviously these frequencies, this is omega m plus omega c, and this will be minus omega c plus omega m, and this one will be omega c minus omega m, and this minus omega c minus omega m, this point over here. Okay, so this is what the modulation does. It jumps, it moves into up in frequency the signal, the original signal. Okay, so let's go now to the lower branch, the water branch that is over here, and let's calculate y2 of omega. Okay, so that's another interesting point here that we find, which is we pass xt through the system h omega. And the h omega has a very nice, very well curious response in frequency, because in terms of the modulus, it doesn't affect at all the modulus of the input signal, because as you can see here, it's always 1, but the phase is changed. For the negative frequency, it adds, it multiplies by an exponential term, which is 90 degrees, which is an exponential term of the type like this, and as we know, the phases add together when we multiply complex figures, complex numbers. So basically this a to jp medio, jp divided by 2 is the same as j. So basically it shifts the phases when the phases of the input signal for negative frequency, it shifts 90 degrees or in the positive sense, and when the frequencies are positive, it shifts by minus 90 degrees, which corresponds to a minus j term. So this filter or this system, a system as this, is called a Hilbert transform, or a Hilbert transformer, or a Hilbert filter, or something like that. Or you can say that the output of a filter is the Hilbert transform of the input. And it has its own name because it's also very important in communications. Why? Because if we call, for example, this signal over here, I don't know, we can call it, for example, x1. X1 is the input, which is x times h of omega. If the input x omega, it will have a certain modulus x of omega and a certain phase, let's call it phi x. H of omega, it's something which has a modulus which is 1 and a phase that is for negative omega, the phase is positive, this one. So what we do for negative omega is we multiply by j, and for negative omega it shifts 90 degrees negative, which is tantamount of multiplying by minus j. So the result, as you can see here, of going through a Hilbert filter is basically the modulus of the input times for negative frequency times j, and for positive frequencies is j. So in other words, if the original signal x of t has this shape, So the output, what we are calling here x1, is take the input x of omega and for negative frequencies multiply it by j. So the negative part of the signal was this was 1. If we multiply it by j here, we will get a j here and minus omega m here. And for negative frequencies, we multiply it by minus j. So for negative frequencies, we just turn around the signal, and this will be omega sub m, and this will be minus j. This is the output of the Hilbert filter to the input triangle. Okay, but in our case, then we need to modulate it with a sinus. Okay, so in this case, y2 will be the convolution of the signal at the input, which is x1 of omega, which is the signal on the left, convolve with the sinus, which you know the sinus is p divided by j, a delta in omega minus omega carrier minus delta in omega plus omega carrier. And don't forget that the convolution in frequency, if it is coming from a product in time, it gets a 1 divided by 2 pi. Okay, so if we simplify here, look at this. We will have this pi here, so we will get 1 divided by 2 term. Okay, and then we have the signal x1 moved to omega carrier and divided by j. Okay, so we can put this over here. Is 1 divided by j x1 in omega minus omega c, because when we convolve the signal with a delta, remember the result is moving the signal where the delta was, and then we will have a minus 1 divided by j x1 in omega plus omega c. Okay, I've just applied the distributive property between the convolution and, in this case, the subtraction. Okay, so basically we need to divide by j in both cases x1, and remember how was x1 was like that. So if we divide x1 by j, what we will get is the same, but taking out the j. So x1 divided by j, we will have here something that goes to 1, this is minus omega m, and this one will go to minus 1, and this will be plus omega m. This is basically x1 divided by j. And then we have to take this x1 divided by j and move it to the right to where omega c is, and move it to the left to where omega c is. That is bring up and down in frequency this signal. So at the end, y2 will have this shape. Around omega c, we need to bring this signal. So around omega c, we bring this signal. Okay, this will be, and then don't forget that we have 1/2 here, 1/2 here, and also on the left, around minus omega c, we'll have the same signal brought, in this case, to the negative frequencies, and also with the plus 1/2, minus 1/2 here. This is what y2 will look like. Okay. So again, what we see is that the Hilbert transform shifts the negative frequencies 90 degrees in the positive direction, and the positive frequency, it shifts them in phase negative j, negative 90 degrees. And then we just modulate that, as you have seen, is just modulation is bringing the baseband signal, which in this case has this shape, up and down in frequency. Okay, but this is what we have. This is y2. We have just modulated this. Okay, let's go now to y of t. So y of t is adding y1 to y2. Okay, so let's calculate here y of omega. So y of omega will be y1 plus y2. So we need to add this signal with this signal over here. So as you can see, there are parts that get twice. For example, this triangle here and this triangle here will add up together and be twice the height of the triangle, and also this triangle here with this triangle here will add up together in the positive sign and the negative axis. But you can see that this triangle here will cancel with this triangle here because are exactly the same height but in negative and the other is positive, and also this part here will cancel with this part here. So at the end what we will have is what will remain as said will be these half triangles. Let's say there will be a triangle here, omega c, which is this part over here but twice the height, so instead of 2 it will be 1, and also on the negative part we will have this part here, which added to the about part, sorry, there is something wrong here. Yes, I did a bad thing, sorry, here, which is the following one. This minus sign, I didn't put that over here. We have to put a minus sign here, which means that y2 is not exactly that, sorry. y2 is this, but with the sign change, so will be like this and like this, sorry. Okay, this will be minus omega c, and this is 1 divided by 2 and minus 1 divided by 2, sorry. So when we add together, the thing that we will left with here, look, this part will cancel with this part, and this part will reinforce. Let's say will be reinforced, multiplied by 2. So in this case, we just need to put this. Whoa, that was a big one. Sorry. Okay. Okay. And also 1. I don't know why it went all the way up to 1.2 millimeter. Okay, anyway, so sorry about that. So I just forgot this minus sign that basically is bringing the same to the left, but also changing the sign. So I of omega will be this function here. Sorry for the thickness. I don't know what has happened. Anyway, that's y of omega. Then we take y of omega, we modulate it, and we will get wy. Okay, so let's go ahead and calculate wy. Wy is a modulation. We know what's going to happen with the modulation, and we saw before. So let me change here. So y1, let's calculate y1 of omega. So what we know is that in time, as we can see in the diagram, y of t is y of t times cosinus omega ct, and the Fourier transform of this will be y1 of omega. And we know it will be the Fourier transform of y of f. The multiplication goes into a convolution with the 2 pi term here in the denominator, and then the cosinus term, which you know is pi delta omega minus omega carrier plus delta omega plus omega carrier. Okay, so this will be the pi, and the pi goes away, and we will have y 1 divided by 2, and then the convolution of the signal with the omegas, we know is just, with the deltas, is just moving the signal where the delta were. And this is what we'll get. So the only thing that we need to do is take y of omega, which is this, and bring up around omega sub c positive and omega sub c negative. So let's go ahead and do that. Here is, we are going to put here w in function of omega. This is omega carrier, so we need this that was in 0, we move it to omega c, so this point will go to omega c, and around that we will have just y of omega. So what we will have is, to the right we will have this part, and to the left we will have this part. Why this left part, this point goes to 0? Because we are moving this to omega c, so this will go to 0, okay, and this will go to 2 omega c. So that's why moving this term to the right, omega c, will end up into this. Okay, this will be obviously 2 omega c, because this term that was omega c moving up into omega c will end up into omega c. And then we need also to move the left part to the to move y to the left, also omega c. Let me write it or draw it in red. Okay, so if I take now this signal and move to the left omega c, this central point will go to minus omega c. Then this point that was in omega c will go into 0, so we will get this point here, corresponding to moving to the left this triangle here, and then we will have around this, this will be minus 2 omega c, so we will have this, okay, and the height will be 1 divided by 2. Okay, this is what we will W1 look like. And finally, the last step is we have to filter this with a frequency omega sub m and an amplification of 2 in this filter. Okay, so let's go ahead. The last stage, which is calculating omega of the capital W of omega. So capital W of omega will be omega 1 of omega times the filter. We pass through the filter, which is multiplying for the frequency response of the filter. So the filter says it goes to omega m. Okay, so if you look into the detail, omega m is exactly this. So the filter, look, has a width which is omega m. So the filter will somehow be situated or placed right over here, and multiplying by 2 what is inside and by 0 what is outside. So if we go and draw this, omega as a function of omega will just be the triangle that I had before. I put this in red, I put this in green. This will be omega m, and the same to the left, and this half, as this is 2, will be 1. And if you take a look, this is exactly what we started with, x of t, x of omega, let's say, or f of x of t. So the result of that is the original x of omega. Okay, or in other words, or W of omega is exactly, W of t is exactly the same as x of t. So we are done. I think it was a nice exercise because it introduced the very important Hilbert transformation that you need how to operate with it. I think that's the major or the most interesting topic. The rest is just being careful with the operations. Don't make the mistake that I made over here of forgetting this minus sign, so that you get basically this spectrum. Okay. Thank you very much for your attention, and I hope to see you in the next video. Bye bye.